This is columns part 9. A phone call ended part 8. Drawback to using your iPhone or the internet access of your iPhone and making a video is that the phone may ring in the middle of the video. But we're close to the end of it, so let's move on. Let's take up where we left off. Okay, we were looking at all these different beams here that weighed anywhere from 12 to 90 pounds per running foot. They had cross-sectional areas of anywhere from 3.5 to about 26 square inches. Okay, the radii of gyration, one with the smallest, well, any beam has a radius of gyration about its x-axis and a radius of gyration about its y-axis. And these numbers are the lesser of the two radii of gyration of each of these beams. So, and the least of all was this one. It was 0.785 inches. The greatest was this one, and that's why this one is only 8.5 feet long to have this slenderness ratio of 84.5, whereas this one, it can be 26.5 feet long and have that slenderness ratio of 84.5. And all these beams had the same slenderness ratio. They're different lengths because they're different sized beams. And because they all had the same slenderness ratio, they all had the same allowable stress of 14,800 psi. Okay, so now let's take a look at one particular beam, this W14 by 61. 61 pounds per running foot, 17.9 square inches is the cross-sectional area. Okay, there's its radius of gyration, 2.45, 107 inches to the fourth power is its moment of inertia. This 26.5 foot beam gave us that slenderness ratio, but we're going to look at a bunch of different lengths. Instead of 26.5 feet, we're going to look at a bunch of different lengths between 1 and 60 feet. So our allowable stress won't be 14,800 anymore, and our slenderness ratio won't be 84.5 anymore. Okay, here we go. These are the numbers for that W14 by 61 beam. Okay, we took a lot of different lengths, anywhere from 1 foot to 60 feet. These are the allowable loads according to the Cornell University calculator. Okay, they range anywhere from 73,700 pounds to almost 386,000 pounds. Okay, these are the different slenderness ratios. If you get above 200, this calculator won't give you an answer. They have to be below that, so a 70-footer would have exceeded the 200 limit on our slenderness ratio. So, and as you can see, a 1 foot long beam has a very low slenderness ratio. Okay, and these are the allowable stresses. You're not allowed much stress when it's 60 feet long, only 4,120 psi, but you're allowed up to 21,550 psi if it's only 1 foot long. Okay, and these are the Euler calculated loads, which obviously are astronomical when you get real short. They exceed the stress limits, the compressive stress limit of the material when you plug in numbers for a short column. Okay, so this is a ratio. This is what I figured out. This is what you get when you calculate the Euler load and divide it by the allowable load here. And obviously it's real high for this short column, over 2,000. But yet when you get close to a slenderness ratio of 200, get on up around 127 to 200, this Euler calculated load gets to be about 3 1/3 times the allowable load. Now here's another column. This is using the formula from the asacaf.com website. We looked at it earlier in an earlier lesson. Let's see if I move this, you can see it there. See, remember that formula, 0.658 to the lambda squared times the yield stress if lambda is less than 1.5. That's the one we use to calculate our failed member. Let's see. Anyway, using that formula, dividing it by the Cornell calculator allowable load gives us different numbers, anywhere from about 1 2/3 to 2.8. The formula from the ASICAF.com website will not allow won't give you a number that exceeds your yield stress. The ASICAF calculated load divided by the Cornell allowable being 3 to 1 here. Yeah, this allowable ratio of almost 3 to 1. Calculated to allowable means the allowable is about a third of what the formula at the ASICAF website gives you. It starts allowing you less and less the longer the column gets. If we compare the W10 by 12 beam with the W4 by 13 beam, we see from the Engineering Toolbox website that the dimensions of these two I-beams are 9.87 inches high by 3.96 inches wide, 4.16 inches high by 4.06 inches wide, web thickness of 0.280 inches, web thickness of 0.190 inches. Okay, when a column fails, it fails about its weaker axis. These I-beams here, they're strong about their X. Each of them is strong about its X-axis. Let's see if we draw an X-axis right there. And this would be the Y-axis. The Y-axis, X-axis, they're strong about their X-axes, but weak about their Y-axes. Okay, here's a picture of an I-beam. See, this is how it won't fail. When you're looking at it and it looks like an eye, and you see the end of it, and you see it compressed until it buckles, well, you won't see the middle of it go up or down. You'll see the middle of it go sideways, like this. It'd be like looking at it with its eye shape. The middle of it goes off to the right here in this picture. And if it's looking like an H, the middle of it will go up or down, because the axis here is the weaker axis. It's the axis with the lower moment of inertia and the lower radius of gyration. This W4 by 13 I-beam is 4.16 inches high by 4.06 inches wide. Its web is thicker than the web of this W10 by 12. Okay, but the web of the W4 by 13 beam weighs less than the web here because it's so much shorter. This web is over twice as long or high as this web. Okay, and since the W4 by 13 beam weighs 13 pounds per running foot compared to the 12 pounds per running foot for the W10 by 12, the flanges of the W4 by 13 there, those flanges are thicker than those flanges. The greater width and thickness of the W4 by 13 flanges result in a greater moment of inertia about the y-axis. It's 3.9 inches to the fourth, here we go, for this beam, and 2.2 inches to the 4th for this beam. The radius of gyration is 1 for the W4 by 13 1 inch, okay, compared to 0.785 inches for the W10 by 12. Okay, this is why a 10.83 foot long W4 by 13 beam has the same slenderness ratio and the same allowable stress as an 8.5 foot long W10 by 12 beam. If a W4 by 13 is only 8.5 feet long and fixed at both ends, it will be allowed a load of 65,500 pounds and stress of 17,100 pounds per square inch. Thus, the W4 by 13 beam will withstand a load of 25% more, which is 65.5 divided by 52.4, or 1.25, and can be stressed 16% more, 17,100 psi, compared to 14,800 psi, which is 1.16, even though its weight is only 8% more. 13 pounds divided by 12 pounds is 1.08. As you can see, when choosing beam cross-sections for columns, a choice would ideally be as strong about its x-axis as it is about its y-axis. This is why many columns are round posts or pipes. Of course, we're not going to use these 12 pound per foot beams to build our airplane, but these tables show that certain slenderness ratios mandate certain allowable stresses, regardless of the other characteristics of the beams. Why did we choose a table of beams that all have the same slenderness ratio of 84.5? Remember that table in Part 8? Because that's the slenderness ratio of our 13-inch long buckled member of the failed tail boom of the steel stork. The slenderness ratio is KL over R. K is the end conditions factor of 0.65 for fixed columns. L was 13 inches, and the radius of gyration of the buckled member is 0.1 inch, a tenth of an inch. So the buckled member's slenderness ratio is 0.65 times 13 over 0.1, which is 84.5. Okay, in conclusion, we see that the actual load of our failed 13-inch compression member of the tail boom that it withstood was 1,022 pounds. In order to do the math, we conservatively replaced our curve shape with a square shape that we knew should not be quite as strong. So the actual load to the calculated load ratio of 1.07 was about what we should have expected. Hence the equation from the ASICAF.com equation that was used to predict a load of 953 pounds seems to be validated. The Euler equation led us to expect our buckled member to withstand a load of 2,650 pounds. See here, I didn't put the units there, didn't have room, but plugging into the Euler equation leads us to expect 2,650, but 1,022 is all we got, so we were led to expect it to be 2.6 times stronger than it was. So, and the stress that Euler would have given us would have been 69,000 psi. Obviously, we will have no confidence whatsoever in the Euler equation by itself, but we'll use it in conjunction with the equations at the ASICAF website. This method seems to be our most reliable predictor of column strength.